everyone. Thank you all for joining us today. My name is Jana Chaaban, and I'll be hosting the webinar for today. I'm the head of Process and Applications Laboratory of Heidelberg Instruments Nano, based here in Zurich, Switzerland. Today we have a very special guest with us, Professor Edoardo Albisetti from Politecnico di Milano. And before hearing from him about his work on phase nanoengineering with the NanoFrazor, I'd like to spend a couple minutes to tell everyone about our latest innovation, the next generation NanoFrazor. So these will be a couple of slides for everyone who missed my webinar in November. And then I'll also be reminding you of the list of webinars that are upcoming. I also wanted to let you know that for my slides, as well as Edoardo's slides, we will record the session. So the recording will include Edoardo speaking and also his PowerPoint presentation. It will not include your video or names. In any case, we invite you to remove your camera for now, to close it. And after Edoardo's session, we will have a Q&A. Some time for Q&A, and during the Q&A, we invite you to open up the cameras again so we can have a better interaction, and you'll be able to directly ask Edoardo all the questions you have, and the Q&A session itself will not be recorded. So I think we can start recording now. Hi everyone again, and thanks for joining the webinar. In the next few slides, I'll be giving you a brief overview of our latest innovation. That is the next generation NanoFrazor system, which we have released just this year. And I'll quickly show you how this tool is ushering in a new era of thermal scanning probe lithography with a special emphasis on parallelization, higher throughput, and also automation. So a quick overview first about our history. So what is the NanoFrazor technology? It's a direct write thermal scanning probe lithography technique. This technology originated from the IBM Research Millipede project, which ran over a long time at IBM Research in Zurich. And the NanoFrazor has been commercial since 2014. In 2018, we joined Heidelberg Instruments, and at the moment we are 25 employees based in Zurich, working on the development and the production of the NanoFrazor technology. This year, we launched our latest product, the next generation modular NanoFrazor. It's a highly flexible tool and 10 times faster. So the way we're tackling parallelization with this tool is by introducing our so-called decapede. The decapede is a multi-tip addition to the tool that features 10 tips working in parallel. These are also fabricated at wafer level, which means that they all work reproducibly well. We've also integrated newer electronics to our tools for faster, lower noise, and scalable operations. And we've also improved our packaging. So at the moment, the decapede comes pre-packaged to a PCB. This makes the loading and unloading of this module much easier on the tools. And instead of using the regular tweezers, we can simply use our hands. I'll show you the first example of the decapede working. Here you have a screenshot of the NanoFrazor software. On the right side, you have a microscope view showing the multi-tip and underneath it the substrate. And you can see how all 10 tips are working in parallel. And in this example, they're working to create a grayscale image. In this cross-section, you see the depth targeted and also the red depth and how they follow each other very well. And you see finally the output of this grayscale image, which is someone I'm sure you all recognize very well. So in this example, we controlled each tip independently, both for the reading and the writing of the feature. But it just so happens they were all patterning the same grayscale image. In the future, of course, what you'll be able to do with the multi-tip is something shown on the left. Each tip can be patterning a separate image. and all 10 tips can be working in parallel, producing grayscale or even 2D features. And these can also be working together with the laser writer that we have integrated in our system. So if you have a base NanoFrazor model, you can either use it with a single tip, the multi-tip with 10 tips in parallel, and you can combine everything also with the laser writer within the same system and on the same material substrate as well. The next generation NanoFrazor also comes in different configurations. You could opt for the tabletop version, which occupies the least space, or you could choose the NanoFrazor with a standalone enclosure, which also limits the outside noise. Or you can also choose to take the entire NanoFrazor lithography system and place it in a glove box and have it be part of a larger cluster of tools. If you're interested in finding out what solution is the best for you, please reach out to us or follow this QR code, which will take you to nanofrazor.com. And after a couple of quick survey questions about your research and desired applications, we can recommend the best software, the best NanoFrazor system for your needs. And that was it from my side. So thank you again for joining the webinar series. I'd like to remind you of the list of speakers we've had so far and the ones coming up. The NanoFrazor webinar series about the next generation system I've already given in November, and the webinar recording is available on YouTube. If you'd like to get the link, please reach out to me. Last week, we also heard from Dr. Aaron Lau and his NanoFrazor engineering of 2D material-based systems. This will also be on YouTube. And today, we have the pleasure of welcoming Professor Edoardo Albisetti, who will start his talk now about phase nanoengineering with the NanoFrazor, both the heated tip and light. So, thank you for tuning in. Edoardo, I think you can start sharing your slides. And in the meantime, I can introduce everyone to Edoardo. So Professor Edoardo Albisetti is an associate professor at Politecnico di Milano, and he's also the co-leader of the Engineering Physics in Nanostructured Materials and Devices group. He also holds a PhD in physics from Politecnico di Milano and has had experience with the Marie Curie Fellowship. His work spans many areas: nanomagnetism, nanoelectronics, and also photonics. And in 2021, he was awarded an ERC starting grant for his novel research. So, Edoardo, we're very excited to have you as our speaker today. The floor is yours. Please go ahead.
Thank you very much, Jana, for the nice invitation and for the very kind introduction. And thanks, everyone, for tuning in. So, today I will talk about a concept that uses the combination of thermal nanolithography and light irradiation to directly craft the physical properties of condensed matter systems of various kind. Before to start, I'd like to thank all the people of the group. There is a fine group. We are located in Politecnico di Milano, so in Milan. And in particular, we are based in the Polyfab, which is the micro and nano fabrication facility of Politecnico, that is a shared facility, also part of the NFFA in part. So some of the things that we do can be, let's say, accessed from outside as well upon application. And you see here the, let me just put laser. So you see here, this is the building. This is another very famous building, probably a little bit more famous than Polyfab in Milan. That is the Duomo of Milano. And it's nice to see that it resembles closely Polyfab, as you can see here. This is where we are located. So in the talk today, I will go through this phase nanoengineering concept that we started a while ago, starting with thermal lithography. And I will introduce the possibility of performing this phase nanoengineering with different techniques, among which the NanoFrazor, of course. Then I will talk a little bit about the possible applications, as Jana said, in the range of photonics, electronics, and magnetism. And I will focus on this last part, so on spin textures and in particular on magnonics. so the possibility to control spin waves propagating in materials using phase nanoengineering. And then about a particular application that we developed in the last couple of years that we just published on arXiv and is currently under review. So let's say the last results of our group. So let me start saying that the motivation of our work is to find new ways of creating nanomaterials, because by finding new ways of crafting nanomaterials, we can actually access new physics and exploit this new physics for giving new functionality to nano devices for a range of applications. These are just a few examples of what happens when someone unlocks, let's say, a new techniques for controlling materials, starting from the, let's say, probably oldest one among these types of applications, so thin film heterostructures, piling up different materials, giving a lot of importance to interfaces to achieve new properties, metamaterials, so having new material properties that arises from nanofabrication, so on basically controlling at the nanoscale the morphology of the material, giving rise to new properties, van der Waals materials, 1D, 0D systems, all techniques and technology that allowed us to go beyond what was possible and find new physics and application. And so what we sought out to do some time ago is to try to explore a new possibility that is the one to directly control the physics of material at the nanoscale by delivering energy really in a local way on the material for triggering physical or chemical transformations. And of course, the material, the starting point of the material are, let's say, conventional nanomaterials, such as thin films, for example. Depending on the dimensionality, we can go from, let's say, 2D materials not intended as graphene, but let's say materials where the plane, the directions in plane are much larger than thickness, so thin films and heterostructures, nanowires where we reduce the dimensionality, or dots. And usually when we synthesize these materials, being them also very complex, but they're characterized by uniform physical properties on the plane. And what we would like to do, and what we sought out to do, is to find a way to let's say, superimpose an energetic potential that we can craft at the nanoscale in a controlled way on top of the material. And this energetic landscape then is used to control the interaction of the material with photons, the transport of quasi-particles such as electrons within the material, or controlling the spins that lie within the materials, all, let's say, crafting at the nanoscale this potential landscape in a grayscale way. So the important thing is that we would like to go beyond the, say, black and white possibilities of conventional nanofabrication and introducing a higher tunability that allows them to have new properties. The idea, going a little bit more in details of what we would like to do about these potentials, depending on the shape and on the spatial confinement of this potential, we can have different effects. For example, periodic potentials usually give rise to grayscale crystals, such as materials where there is a, let's say, superimposed periodicity that is seen by outside as a new uniform properties that is different from the uniform property that was before, introducing this energetic landscape, or metamaterials. On the other, let's say, part of the spectrum, you have confining potentials, such as, for example, wires, dots, or in general, handmade circuits on the material. If we think about electrons, by changing the conductivity of the material locally, we have regions that can conduct, regions that can be semiconducting or insulating. And by, let's say, controlling the flow of electrons within these materials with such different properties and with a high contrast between the properties in different regions, we can control the flow of these particles, and, for example, having nanoelectronics. Or if we're interested in waves, such as us, for example, that we're interested in spin waves, you can use confining potentials acting as waveguides. Or more complex potentials, such as asymmetric potentials that cause quasi-particle waves to propagate, for example, only in one direction and not the other one. These are just quite general examples that then we, let's say, take and we apply to different scenarios. And the important thing of this is that for producing this energetic landscape, we need somehow to transform the material. And a very clean way to do it is to deliver energy to the material in a highly localized way. And of course, the first technique that we use for doing this was thermal nanolithography, because it's really good for that, because it's clean. You don't really change the atoms within the material. You change maybe the disposition of the atoms, so you change the phase, or you can trigger reactions at the nanoscale, being really precise in the temperature. And if the reaction has, let's say, a transfer curve that is not super steep, you can then tune the reaction by tuning the temperature. And thermal lithography and the NanoFrazor more recently, it was really good in tuning, let's say, the temperature through the of the reaction. So if we go and check the features of thermal nanolithography for this particular application, we got the mechanism that is heat transfer from a really pointy tip. I will not go too much into details, because I think that we already know a lot about thermal lithography in the series. But it's really important, the heat transfer from the tip to the material. Regarding spatial resolution, it's very good, in principle, sub 10 nanometer, and we are in the microsecond range that is related to the time that the tip hits and cools down. So we're kind of, let's say, limited both by the cooling time of the tip and the movement, let's say, of the sample, but we're mostly in the microsecond time range. Regarding the dimensionality of the patterns, of course, as we know, especially using resist, we can do 2.5D patterns. So starting from the surface, we can control the pattern in the Z direction by moving up and down. In phase nanoengineering, we can do we go directly to the material, so we don't have the resist in between. So it's somehow a little bit more complicated to the 2.5D, because we cannot really move inside the material. But tuning the temperature or other parameters, we can achieve something that resembles that. So the dimensionality is 2.5D, and in any case, it's let's say really focused on the surface of the material. Of course, especially for phase nanoengineering, I know that for the resist this is not the case, but for our application, the biggest limitation is the limited temperature that we can reach. Especially in contact with a material that may be a metal, so it really dissipates heat really well. So the actual temperature, interface temperature between the tip and the material usually is quite lower than what the night calibration curve shows. And so if we have to trigger transitions that happen at higher temperature, we are kind of in trouble in this sense. But still, most of the reaction we're interested in are within the range, let's say. And if one pays attention to the substrate and to other things, one can usually reach the temperature that wants. Another technique that now is available is also continuous wave laser writing. In the case of NanoFrazor, is a UV laser, say 405. Nanometers, and in this case the mechanism is completely different. So it's linear light absorption, the most, let's say, common mechanism that is used, again not with the resist, but directly in the material. And so the technique is really efficient if the material absorbs UV light efficiently. On the other hand, if the material is transparent, you don't actually have almost any heat up of the material. So in this case, the material is even more important. The type of material is even more important to trigger the transition, coupled with the technique itself. Of course, space-time is slightly different than thermal nanolithography. So we have a definitely worse spatial resolution because we're usually diffraction limited by the fact that we have free propagating electromagnetic waves. So we're limited by the diffraction by roughly the wavelength of light. And the time, usually exploiting thermal effects, we can go down to nanoseconds, Q-switched lasers, for example. So we're now building a system that uses nanosecond lasers. Usually the short is the pulse, the more confined can be the heat generated. So usually going to low times is a little bit better for spatial resolution. So it's good to try to go towards nanosecond lasers. Of course, the mechanism, still being linear absorption, starts from a very top surface. So it's somehow similar to what happens with thermal nanolithography. And it's usually, not always, but usually triggered, at least in our case, by heat. So the UV laser is absorbed, it hits out the material, and then it's the heat that produces the transition. But sometimes it's not the case. So sometimes you have directly species that react to UV photon absorption. So in this case, you don't even need heat, but you have a transition that is directly triggered by the UV light without needing, let's say, to go through the phonon relaxation and local heating. There's a caveat. We are diffraction limited, but somehow if we use transitions that are really peaked, as I will show you later, we can go well below diffraction. And I think that this was also observed with the resist of the NanoFrazor. So somehow, if the transition that we use is not a gradual one, but has a single steep transition at a certain temperature, then even if the beam is Gaussian, then tuning the power, the focus, we can really get to resolution that are way smaller than the nominal focus or beam waste of the laser that is usually about 1 micron. Of course, all this is surface based and 2D. There's the third technique that actually, let's say, goes a little bit more towards the volume. This is ultra-fast laser writing. That is usually femtosecond laser writing. It uses a different absorption mechanism that works well with transparent materials. It uses nonlinear absorption. So in this case, it's not a single photon that is absorbed, but it's a multi-photon transition. And it has some advantages. For example, the spatial resolution is somehow below the say around 100 nanometers, usually, depending on the application, but can be below diffraction. Time scale is femtoseconds, so we are definitely triggering a different regime for the material for light matter interaction. So we're not only, let's say, using heat, but we're also triggering other types of reactions, ionization, micro explosions, microvoids. So you can do quite different things. The important thing, of course, the big advantage is that you can go in the volume. So moving the focus within the volume, you have a voxel that can be moved also within the material. If the material is transparent and so linear absorption is negligible, you can write fully 3D things within the material. Of course, this is used, for example, in 2-photon polymerization machines for 3D printing, but it can be used also for changing the properties of the material. And so I think it's really interesting in this case as well. There's an issue here that combining surfaces and volume writing is usually quite complicated. So it seems beautiful that you can go within the volume, but if you want to write in the volume, but being still quite close to the surface, then things gets a little bit messy because surface transitions are usually different than the volume ones and usually happen at lower energy. So writing in the volume without writing the surface is kind of tricky. But it's something to keep in mind, but interesting. And about this, of course, coupled to the techniques, there must be the right material. So materials that are sensitive to these transitions, to this type of mechanisms that we were talking about. And throughout these few years, we identified 3 categories, starting from the first one, that is the one where we started working. That is thin film heterostructures. So if we have thin films and we couple them, we stack them one upon the other one, then volume effects gets less important and interfacial effects gets a lot of importance. And by heating up or irradiating the material, we can control these interfacial effects. Some examples are, for example, with ferromagnetic materials, antiferromagnetic materials. So in the field of magnetism, there's a lot of things happening at the interfacing. The interfaces, if the materials have a different magnetic ordering, for example, this is a ferromagnet and an antiferromagnet, and there is an effect here at the interface that allows us to control the direction of the magnetization in the ferromagnet, for example. And this is triggered by heat. So the first thing that we did was to heat up the material and use, let's say, the thermal lithography for controlling the spins within the material. Other classes of material that we started to study more recently are actually very interesting and very general as well. So one class is complex metal oxides. So it's a super broad range of materials where you have usually transition metals that are the transition metal oxides that are quite complex in the unit cell. This is an example. It's called yttrium iron garnet, and we'll talk about it a little bit later. It's a magnetic material, but due to the complexity of the unit cell and to the fact that there's oxygen, it's really sensitive to transformations driven by heat and by light. So it's really interesting to use. This is just one material, but the class of materials is actually immense. There's superconducting materials, magnetic materials, topological materials, piezoelectric materials. So it's really broad range of materials that can be investigated. Other materials that are more probably were quite also probably closer to applications. It's phase change materials, for example, germanium, antimony, tellurium alloys, whose optical and conductive properties change abruptly when the crystalline phase change. And the crystalline phase change is actually triggered by heat. So what we are studying is also how to control this transformation for patterning different properties of material. It's a concept that is widely used in photonics, for example. It's actually the CD-ROM, where it's based on a similar mechanism. But also in electronics and for memories is really highly investigated. And so basically now we have these classes of materials, but the important thing is what we would like to do with these materials. And so if we take this imaginary triangle of interesting things that can happen within the material, and we have at the three corners of the triangle, the charge associated with electrons, the photons, and the spins. And we have the three branches that we're interested into. So when we are controlling the spins of material, we have nanomagnetism, and the dynamics, it is magnonics. When we control the charge, we got electronics. When we control the interaction of the material with photons, we have photonics. And then we have the hybrids, let's say some of the hybrids, there's more. But for example, if we control the spin to charge conversion, we have all spintronic effects, photonics and electronics, we have plasmonics and magneto-optics. But let's stick with these three that are the ones that we are most interested into recently, starting from the nanomagnetism. So as I was saying, controlling the direction of the magnetization, also known as spin texture of the materials, allows to design devices for memory and computing, for example. Or once you have designed your spin texture, so your magnetization direction, you can control also the dynamics. So how this magnetization moves in the roughly gigahertz range when it's excited by external perturbations. And these are spin waves that propagate within the material and can be used, as I will show you later, for computing. But also in the electronics, sticking to the possibility that we can access with phase nanoengineering and we are exploring, let's say these days, we can have a way to control the conductivity of materials and write nanoelectronic components such as nanowires, dots, or tunnel barriers, really tiny ones directly on the material, or to craft the properties of the material to give it properties that it doesn't have at the beginning, such as nonlinearity. That is a property that is highly sought for in neuromorphic computing, for example, and so create new materials that act as physical reservoirs. In photonics, we're actually something that we started really recently. But of course, the idea of having grading metamaterials or metasurfaces that let's say interact with light in a let's say new way when the material is structured, and the idea to have a material that can be tuned really precisely point by point opens up a lot of possibilities that we are exploring. So in the next part of the talk, I will focus on magnetism, in particular on the dynamics. So on spin waves, and on spin waves in particular in this material that is called yttrium iron garnet, that is a complex oxide. And I will show you some recent results that we had on this. So to start from magnetism. So when we have a thin film, for example, of ink, of this material that we would like to study, and we apply an external magnetic field, this red arrow, then we have all the spins that align with the field. And so we have what's called a monodomain, so a magnetic material that is a single magnetic domain where the magnetization in this case points out of the plane vertically. And stays there. So if we are ideally at 0 Kelvin, then nothing is moving. But as soon as we add some thermal energy or some localized magnetic excitation, such as in this case, in the form of a magnetic field that is localized there in the green region and oscillates at a certain frequency that is in the gigahertz range, then we're basically taking the spins out of equilibrium. And this perturbation is actually not localized to the spin that we excite, but then propagates within the material in the form of a wave that is a spin wave. And so you see that this perturbation that has the form of a precession of the spins around the external magnetic field direction then propagates within the material. And there are a few nice properties of these waves. This is, for example, what they look like when we measure them at the synchrotron. This is spin waves with a 300 nanometer wavelength at 1.29 gigahertz that propagate within a ferromagnetic material. Of course, they're waves, so they have all the properties of the wave, wavelength, dispersion. But the interesting thing about spin waves that makes them very interesting for applications is that they have a really low wavelength, submicron, such as in this case, where it's 300 nanometer, in the gigahertz frequency range that is interesting for data processing and signal processing. And so you can imagine to have analog systems, or in any case, wave-based system, where these waves can be shrunk to the size of a chip, which was something that was, let's say, not very easy to do with electromagnetic waves that at those frequencies are in the millimeter range. So you cannot do that with electromagnetic waves. Spin waves are a possible interesting way to do that. The other interesting thing is that with spin waves, as you see in this video, you don't have charge motion. So it's only the spins that rotate in place. Let's say they precess in place, and so there's no ohmic losses because there's no let's say motion of charge within the material, and which means that in principle it's possible to do really low power consumption devices. That this times is a really important issue. The thing that makes phase nanoengineering interesting for magnonics is also that spin waves are highly tunable with the magnetic properties of the material. So if we have a way to control the magnetic properties in the material, the nanoscale, or really precisely, then we have a high chance that we are able also to control spin waves in a really important and, let's say, way. Just a couple of applications to give an idea of what people are studying right now in the field of magnonics. As I was saying, is basically a way to have a wave-based computer on a chip, so a really small wavelength. And you can have different ways of computing. You have Boolean computing, somehow a little bit more conventional. So in this case, for example, you have a majority gate where you have 3 waveguides that meet up in this point. You send spin waves in, and you have that the output is 1 or 0 depending on the majority of the inputs. So in this case, for example, there's only one 1 and the other 2 are zeros, and so you get a 0 in the output. If you have 2, you have 1, and if you have 3, you have 1 as well. So it's basically a way to do a majority gate using wave-based computing without needing to have cascades of transistors. So in a certain sense, people demonstrated that it can be really energy efficient and also compact. On the other part of the spectrum, there's the analog possibilities given by the fact that spin wave interference, of course, happens gradually within the system. In this case, for example, is a nice example of a spectrum analyzer where you have a signal with different frequencies. You feed the signal to the system in the form of this antenna that excites spin waves at those frequencies. And then naturally within the material, this interference pattern occurs And if you engineer the material properties, then different frequencies go in different spatial locations, and then you pick up the signal and you know the amplitude of the original signal at that frequency. So basically you analyze the spectrum in an analog way without having to pass through Boolean logics, and so possibly lose energy in doing that. Other more, let's say, exotic or non-conventional computing concepts are related to neuromorphic and in particular reservoir computing. Recently, a lot of proposals were made to use spin waves for reservoir computing using different systems such as nanomagnets or spin ice systems. Are really interesting proposals. But this was just to give an overview of what people are studying in the field of spin waves. Recently, there was let's say, quite a new development in the field, not only in the field of magnonics, but in general in the field of nanomagnetism. That is the possibility to add three-dimensionality to the structures and to the physics of what we are studying. And the idea towards this three-dimensional nanomagnetism and magnonics was to study new physics, to induce new functionality in devices by realizing three-dimensional systems and studying them with specific techniques that were 3D sensitive. Some examples here, for example, three-dimensional magnonics that, let's say, encompasses a wide range of applications, ranging from different types of materials to different ways of studying the spin waves through the volume of materials. Another big example these days in the field is 3D spin textures. So spin textures, so magnetization orientations that are non-uniform through the thickness, through the volume of the film. And so you have fully three-dimensional magnetic structures, curvilinear nanostructures, three-dimensional nanostructures. So finding techniques that are able to create such materials, such devices, with the final goal of building 3D integrated devices where it's the three-dimensionality that gives a higher functionality to the device itself. And in the field of magnonics, there's a big problem because there's a almost complete lack of techniques for building three-dimensional magnonic materials. And this is where we entered and we tried to see if there was a way to use phase nanoengineering to overcome this. So to find a way to build three-dimensional magnonic materials and devices using phase nanoengineering. And the reason why it's so difficult to do it is because the best material that there is for magnonics is this one, that, as you can see, is quite complex, is a very complex unit cell, is a transition metal oxide, where you have a very complex unit cell, and the material itself is an insulator electrically, so it doesn't conduct electricity, and it's a ferrimagnet. And the reason, so ferrimagnet means that there are two sublattices with a magnetization that points in an opposite direction. And since these two sublattices have a different magnetic moment, when they sum up, even if they are oriented one on top and the other one on the bottom, there is still a net magnetic moment that makes them susceptible to magnetic fields, for example. And the reason why is that iron, that is the magnetic ion that lives within the yttrium iron garnet unit cell, actually lives in two different coordination sites, two octahedral sites and three tetrahedral sites. And so when you put everything together, you end up having a magnetic material. An important thing about this material is not really the fact that it's magnetic, because there's a lot of other magnetic materials, especially metals, but it has the lowest magnetic damping ever recorded. And magnetic damping is what kills spin waves that propagates within a material. So when you have a metal and you launch a spin wave, after a few microns, the spin wave decays exponentially because of losses of the energy of the waves, for example, in the lattice. And so it's really important and critical to find materials where spin waves propagate really for long distance. And in yttrium iron garnet, they propagate for millimeters. That is totally acceptable for doing nanoscale chips. So millimeters is definitely very good. And so what we would like to do is to find a way to preserve this super nice, long, coherent propagation of spin waves while fabricating devices and while controlling the properties of this material. So conventional fabrication for IG uses the, let's say, usual techniques that are used also for metals and in the let's say, microelectronics industry. So electron beam lithography, ion beam etching, photolithography, wet etching to create physical structures within the material, or more recently, ion beam irradiation that directly modifies the material by irradiating with high energy ions. But let's say both these techniques have some disadvantages. So they locally usually destroy the material, especially photolithography and electron beam lithography, because you're basically removing the material. You have a lot of problems with the edges of the material because you really would like to have nanostructures, but when you start having really nanostructures, the borders of the structures happen to have a higher importance with respect to what's inside, that is the material that remains good. And so you start having a lot of issues with the roughness of the borders, for example. And all this leads to damping degradation. So to the fact that the optimal material properties actually goes away. And of course, there's no 3D capability. So what we try to do is to use phase nanoengineering, and in this case with direct laser writing, in particular with the UV laser of the NanoFrazor, to see if we were able to write the IG, so to change and control the magnetic properties of the IG. And so what we did was to irradiate the material point by point by tuning the laser power, the focus, and we're focusing on one material that has a 1 micron thick IG on a GGG substrate. And the substrate is really important because this is the substrate that is normally used for growing this type of material that leads to really high quality material. And it happens also to be UV transparent. So one of the nice things that we found out is that if you flip the chip and you write from the back, you can also write on the bottom surface of the material because the GGG is completely transparent to the UV radiation. And so you have a way to basically write the material. Now we will see what it means to write this material, but both from the top and from the bottom, aligning the patterns. An important thing is that in this case, what we found out was that the depth of the pattern was tunable with the laser power. So we were able to write different, let's say, graded quasi 3D patterns by changing the laser power. So going a little bit more in depth, this is what it looks like, the material. So this is the stripe domains measured by magnetic force microscopy, where the magnetization in the materials in the stripes lies in the direction of the stripes and oscillates, let's say, top, bottom, and the white dark contrast that you see here is the oscillation of the magnetization, a little bit outside the plane and a little bit towards the plane. This is the non-written film where the periodicity of the stripe, this is related to the magnetic properties of the material, is 1.6 micron. Then what we found out is that increasing the power, at the beginning, nothing happens pretty much until this point. And then abruptly, we have a complete change in the domain structure of the material here. And you see that the most striking difference is the periodicity of the stripes that are created in this circular pattern that pass from 1.6 micron to 0.6. And in magnetic terms, this is a huge difference. So at the beginning, it was not so easy to understand what was happening because the change was much higher than what expected and what we could see with simulations, for example. And then we see that by increasing the power above this threshold value, the periodicity of the stripes slightly increases and also the magnetic contrast increases. So it means that there's something gradual happening when we go above the threshold. Something else that we tried was this backside patterning that I was telling you about. So by flipping the chip, so first we pattern vertical lines from the top, then we flip the chip and we pattern horizontal lines. And then we flip again the chip and we perform MFM, magnetic force microscopy, to check what happened. And we have buried structures. And in this case, this is a crossbar configuration where if we tune the thickness of the film and the power of the laser, we can kind of tune the, let's say, interaction region within the volume of the film. And something else that we checked was the minimum feature size as a function of the power. With a single laser shot, we got, with a lot of tuning actually, but down to 100 nanometers. That is roughly 10 times below the focusing size of the laser on the material. And I will show you later why we were able to achieve such a small feature size. Something else that we were eager, let's say, to try was what happens if we continuously tune the power point by point. So what we did was, let's say, a sinusoidal two-dimensional map of powers. And then you see here what happens when we pass from low power to high power. Low power is here, high power is here, and we pass through a sinusoidal change. And we go from basically something that resembles the background, so large stripes, up continuously up to these small stripes with high contrast. So we were able to somehow tune the magnetic properties of the material in a continuous way. And what we found out later, actually, a little bit later, is that what we're doing here is we tune the depth of the patterning in a really highly controlled way. If we go and check the topography just to see what's going on, we see that corresponding to that really huge change in the magnetic properties, we have quite a small change in height, which is reproducible and follows the power map. So in the regions with high power, we have a 5 nanometer roughly higher topography than in the lower power regions. And this is consistent with the fact that somehow we are changing the strain the strain of the material by irradiation. And so what happens is that it slightly changes the reticular the crystal say the lattice parameter, so that at the end we have a tunable height of the material that if we make the calculation turns out to be a few percent that is compatible with strain within the material. But to actually understand what's happening more quantitatively to the magnetic properties, we have to acquire hysteresis loops. Hysteresis loops are the way that we have to measure magnetic properties. And in particular, what we did was to acquire in-plane loops. So we apply an external magnetic field and we measure the magnetization using a laser, using the so-called magneto-optical Kerr effect. And we see a tunability of the hysteresis loop that changes a lot from the black curve, that is the pristine, that actually saturates around here, around 3 millitesla, to the higher power patterns that saturates at 60 millitesla. So if we plot the saturation field, so the field that is needed to completely reverse the magnetization, you actually get a 20%, 20 per enhancement of the saturation field. And if you run saturation, this means that what is happening is actually that we are enhancing the so-called out-of-plane magnetic anisotropy of the material. That is the properties that tells the material magnetization to stay out of plane. And this is a really important properties because it changes the spin wave dispersion a lot. So the possibility to enhance by 30 times the out-of-plane anisotropy simply radiating was kind of exciting when we found out, let's say. And you can see the same also in the MFM image as a function of the field, because in the pristine film, you get that as soon as you increase the field, for example, here we have 5 millitesla, the magnetization disappears, while in the pattern film, you need much higher field to make the domains disappear, 600 almost. So you basically see the same at the nanoscale with the MFM that we saw here with the hysteresis loop. But we wanted to check that actually this hypothesis of the three-dimensional patterning was let's say was actually what was happening. So we made big patterns and then we aligned a dicing saw to cut a cross section of the material and watch what happens at the SEM in a cross section. So here you see the same cross section of the material. We see the substrate, the side of the egg. This is 1 micron thick, and the surface. So it's kind of tilted, so you both see the side and the surface as a function of power. And we see that we can somehow have a modification in the material volume that is depending on the power as we expected. And if we plot this as a function of the laser power, we see that we can control it quite linearly in a certain range. After a while, so after 30 milliwatts, the material explodes because there's too much strain, and so it detaches from the material. But in a certain range, we have a quite linear response, which means that we can tune it quite well if you are careful enough, even if the laser power range is quite low. So we have to be really precise. And then we took this measurement of the thickness of the transformed material and put it into micromagnetic simulations, and actually found out the magnetic MFM that we were measuring. So we were happy because it means that this is actually what is happening. So in the pristine, we see large stripes. Then we have in the low power, we have only a small modification within the volume, and we have a small layer here that supports these small stripes that we saw in the MFM. And then if you go to higher power, you have a much thicker layer, transformed, let's say, layer that supports larger stripes. So this is what we found with combining simulations and the measurements from the SEM cross-section. But what we're interested into are spin waves. So we went on trying to see if the spin waves were actually modified within the pattern. So what we did was to pattern big structures, so big squares, and then to put an antenna on top that is needed for exciting spin waves, and then measuring optically with a technique that is called Brillouin light scattering that was performed by our colleagues Silvia Tacchi in Perugia. And what they did was to measure basically as a function of the power of the pattern, the spin wave spectrum. And basically the peaks are the presence of spin waves at a certain frequency here. And you see that below threshold, so below, let's say, the appearance of those small stripes, pretty much nothing is happening. So the modes are the one of the pristine film. But then as you go above threshold, you have one peak when you have a thinner, let's say, transformed layer. That is a new spin wave mode that propagates within the layer that we created. And if you go to higher power, slightly higher power with the thicker transformed layer, then you have more peaks that are related to other spin wave modes that travel within the material and within the volume of the material that now increased from 100 nanometer thickness to 200. So you have more spin wave modes. And so you have actually a way not only to control the spin texture, but also to control the dynamics and induce new spin waves within the material. And so for demonstrating applications, we created what's called a magnonic crystal. So we took the NanoFrazor laser and we patterned single dots within the material with a certain periodicity. And then we went again with Brillouin light scattering to measure a two-dimensional map of the spin waves within the treated area. So here. And we could see that we could actually create new modes within the material that were spatially localized in the regions where the spin wave intensity is maximum, which is the green, yellow regions, and on the contrary, create regions where no spin waves were present. And this is because due to the interaction of the propagating spin waves with the regions with enhanced magnetic anisotropy that we created with the laser. So the last thing that was remaining is actually to understand what was going on to the material. And so we went to do some structural characterization via micro Raman spectroscopy. And what we saw that was surprising to us was that the Raman spectra were quite similar one to the other one, even above threshold. And also the optical image doesn't show almost anything, also above threshold. So it seems like that we are not creating big changes in the crystalline structures of the material. And this was also confirmed by electron backscattering diffraction measurement that showed that the crystalline orientation of the irradiated material is identical to the one that was not irradiated. And also reflectance measurements show that something is happening only in the UV range, but almost nothing happens in the optical range, which means that the structure of the material is quite intact. The only thing that we observed was broadening towards the left of some of the peaks of IG that is compatible with the creation of oxygen vacancies and strain within the material. But this was surprising and also, let's say, hopeful, because we don't want to really change too much the good magnetic properties of IG. So the fact that we were able to retrieve the original crystallographic orientation and crystalline quality was a good sign. And so what we went on is to do simulations to understand what's going on to the material during irradiation. And so we simulated the power density that was absorbed as a function of thickness and the temperature that was reached within the material. And what we found out was that at the powers and power densities, let's say, that we were using, we were able to quite easily reach the melting temperature of Ig, that is 1830 Kelvin, in a nanoscale region that is confined at the surface. And if we increase the power, this 1830 temperature line actually shifts a little bit like this towards the bottom. So what we think is happening is that we're actually melting and recrystallizing the material locally. And depending on the power, we are reaching different depths because we are reaching, let's say the melting temperature is reached, the melting temperature threshold is reached well within the material. And this also explains why we can reach this 100 nanometer spatial resolution, because this is indeed a really threshold transition. So it's a melting that happens at that precise temperature, more or less. And so what is going on is that if we have a Gaussian beam and we tune the beam so that only the peak actually overcomes the transition, then we can achieve subdiffraction resolution in the final pattern, because we are convolving the Gaussian beam with a really peaked transition. So this is a nice way, and I think again that was also seen probably with the NanoFrazor races with the PPA, because it is a nice way to achieve subdiffraction limit with transitions that are peaked. Of course, we're working also with materials that do not have such a sharp transition, but have more gradual transition. And in that case, the spatial resolution is lower, but the tunability is a little bit higher. So it's a trade-off between, let's say, spatial resolution that you can reach and tunability of the transition. And in this case, what we found out, even if it's really difficult to be quantitative and sure, is that the tunability is in the depth more than in the change in the properties that we have in the transformed region. Okay, so I think I finished. So in conclusion, I showed you the concept of phase nanoengineering and the three techniques that we are exploring, let's say, and possible materials that we are studying. And the interesting thing to us is that it can be used to many different systems. It's really versatile. It can exploit different mechanisms, and also for different applications. So we think that there's a lot to study, let's say, in this field. And in particular, I showed one our last result that was a three-dimensional control of magnetism in oxides, in particular yttrium iron garnet, that allowed us to control the out-of-plane anisotropy and enhance it by 30 times in a nanoscale confined volume through the thickness, and to use it for a variety of magnetic devices. With this, I thank you a lot for your attention, and I would like to thank also the two people that most collaborated and performed actually the work that I showed you at the end. So Valerio Levati and Matteo Vitali, and all the group for the help. That was actually a collaborative effort, and also collaborators from other universities. And again, you for your attention, and Jana again for the invitation. Thank you.